We've been looking at equipotential surfaces, and we've described them as being points where the electric potential is the same. We're now going to have a look at, in a little bit more detail, at what electric potential actually is. And in order to do that, we're going to start off with two positive charges. And it's probably easiest here to think of one of them as being fixed in space, so it's not going to move, and the other that can move throughout space. And those two positive charges, we're going to consider them as being separated by an infinite distance. And the reason for the idea here of infinite distance is we're basically saying that when they're that far apart, they won't really have any effect on each other, and so effectively there's no interaction between the two. So what we're really kind of looking at is we've got, say, a positive charge over here. Around that positive charge we'd have an electric field that would extend out in all directions. I'm only drawing the close to the charge, but we know that would extend further and further away. And we'll call this charge capital Q, and then over here somewhere at some large distance away that's effectively infinite, we'd say that we'd have charge Q. Now if we imagine a point, say here somewhere, we'll call this point X. If that charge lowercase q, so if little q is brought to point X, what we're going to see is that some work is going to need to be done on it, and the reason for that is because it's we're moving it against the electric field around capital Q. So it's being moved against the field, and again that wording against meaning in the opposite direction too, against the field around big Q. Now if we moved it to point Q, we would say then that point X, we would say then that Q has electric potential energy. So at X, Q has electric potential energy, and you might want to make we will actually come back and look at the gravitational equivalent, but you've probably come across it before, being gravitational potential energy. So the reason why it has electric potential energy is due to its position in an electric field. We will get into more detail about electric potential energy in 10.2, but we'll just mention it on the way through here. So we'll come back to this idea and explain it in more detail. Sorry, not in an electric field, in the electric field around Q. And if we wanted to look at how much electric potential energy is stored there, we can basically just identify that it's the same amount as the work done in moving charge Q to X. So we've got this idea that work and energy are basically the same idea, same concept, and so we can use that the amount of work that we do is equal to the amount of energy that's gained. Now we need to understand that in order to define electric potential. So if we knew what that charge was, we could measure the energy needed, and then we could do something with the charge as well. And that's something that we're going to do is about electric potential. So electric potential, instead of worrying about exactly how much charge, we're looking at the energy per coulomb of charge. when moving a charge from infinity to some point in a field. So we're not so much worried about exactly how much charge there is, we're worried about the amount of energy per coulomb of charge. And we can write that in equation form as V being equal to W on Q. Now V is the electric potential, and electric potential is measured in volts with the symbol capital V. W is the work done, and that's measured in joules, and Q, capital J, Q is the charge. And that's in coulombs. So that's if we're looking at the electric potential at a point in a field. More commonly, we won't really be bringing a charge from a point at infinity to somewhere in a field. We'd usually be moving between 2 points in a field. So if we go back again and have a look at this idea of the charge capital Q with its electric field around it, would probably be more interested in, say, moving a point from this point in the field to this point, and we'll label them point 1 and point 2. Now, in that case, we're more interested in moving between the points. And so in that case, we're not actually looking at electric potential, we're looking at potential difference. So we refer here to potential difference. Making mistakes. And very simple adjustment to the equation. We're now not looking at the electric potential anymore, as I said. We're looking at the potential difference, and so we'd simply just write delta V is equal to W on Q. So there's still going to be a certain amount of work needed in order to move from point 1 to point 2, and that amount of work compared to the amount of charge will tell us the potential difference. And important to note here as well that delta V is then just the difference between the potential at point 2 and the potential at point 1. There's one last point to make about electric potential, and that has to do with the sign of the charge that we're dealing with. I'm just going to reproduce this diagram showing a positive charge with field lines directed away from it, because you'll recall that field lines show what happens to a small positive test charge if it was placed in that region. If we were considering a point out here somewhere, let's call it point A, and at this point it's effectively at an infinite distance, the potential out here would be 0 volts. Now, in order to do work on that charge, we have to move it against the field, so we'd be moving it in this direction, and we might drag it into this point here, say, and let's call it point B. The potential there at point B might be, say, 10 volts. Now, to do another bit of work on it, we might move it into halfway closer than what point B was, and the potential at C would then be 20 volts. So you can see there that the potential is increasing the closer we get to the positive charge. If we deal with a negative charge, the field lines are now in the opposite direction, so they're going towards a negative charge, again, because field lines show what happens to a small positive test charge, shows the direction of force on a small positive test charge. If we again go to this point out here, at point, let's call it point D, again, that point is at an infinite distance from that negative charge. The potential there is still going to be 0 volts. Now though, if we had a charge there, we actually don't need to do work on the charge because it's now moving in the same direction as the field. So if we got into a point here that was point E, the potential here, we would say that it's actually negative 10 volts. So that negative indicates that we've actually lost energy. The charge has actually given up some of its energy in order to get to point E, because it's being attracted to this negative charge. If we wanted to do work on the charge to get it back to 0 volts, we'd actually then have to move it back in this direction, so against the field, in order to get it back to 0 volts. That means that if it was to move further in again, say to point F, the potential at point F would be negative 20 volts. So you can see there that if we're doing work on the charge moving from F to E, we are increasing the potential the same way that as if we're doing work moving from B to C around a positive charge, we're increasing the potential. The important thing to note here too, though, is that whether it's a positive charge or a negative charge, at an infinite distance the electric potential is 0.